Assalamu alaikum. My name is Muhammad Saib Nabrar Prohor, and this is a task assigned by data synthesis for second round, and I have got set A. So for question number 1, I got an AVL tree storing numeric values. So I have to design an algorithm to efficiently return the sum of all values within a given range. So let's go ahead and imagine that these are the values of my AVL tree. So a AVL tree is basically a binary search tree or BST that balances itself for keeping the branching factor from -1 to 1. So let's draw this for portraying my thought process how I came up with the solution. So the tree is this 20. I'm sorry for my drawing. Then the left node is 10, then the left node is 5, then the right node is 15, and here the right node is 30, left node is 25, and the right node is 35. So basically it's a AVL tree, and now my task is that I will have a range from L to R and find the sum of the keys within that range. Suppose I have a range from 17 to 34. That means the values here are within 17 to 34 are 20, 25 and 30. That means these are the values I need to bring out the sum of. So if I follow through a basic summing algorithm, then I have to check through all the keys, like I have to check here, 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 here to check that if it's within the left and right range, and it will take a lot of time. So to make it more efficient, I have come up with a solution which is node augmentation. So here let me erase the current pick. So to make it more efficient, I have come up with a solution where I will augment the node which will have the key 20, then the minimum value of the subtree, maximum value of the subtree, and the sum of the subtree. So this will be my main node, and I augmented the node to keep those value within itself. So by doing this I will have here 10, here 5, here 15. So for this node my minimum value is 5, my maximum value is 5, and my sum is also 5. Same goes for here. My minimum value is 15, maximum value is 15, and sum is also 15. So for this node my minimum value is 5. Like comparing those, minimum value is 5, maximum value is 15, and sum is 30. So these are the values stored, and same goes for the right tree also. So you can ask me that how it benefits the algorithm to be more efficient. Right now, because of that, I can check my left range if the minimum value is, or so for the left range I have to check the maximum value if it's less than L. So if the maximum value of a subtree is less than L, then I don't have to explore that tree. I can just prune it so that I don't have to explore that, and this saves a lot of time. You can see that this is a small tree, but if I have millions and millions of levels of data then it is very efficient and it prunes that level. Also for the right tree, if the minimum value of the right tree is greater than my right range, that means that it is out of my right range, as it is just increasing from the value. By doing that I can just prune that node, and I don't have to explore that. So by doing this I have solved the issue. So let's explore the code where I have written the solution. So here I have augmented the nodes. This is the basic nodes, and here I have augmented the nodes where I have used subtree sum, subtree minimum, subtree max. Right now it's just keys. Later, sorry for my cough. Here the update function updates all the variables within those nodes, and it is also updated by me. And here the are the basic function which are used in an AVL tree, and here is my solution. So at first I give the function the main node, left range and right range. Then if it checks if the node is there or it's none. So then by if it checks out, then I check that the maximum value, if the maximum value is less than left range, that means it's 0. I don't have to check that those three. Also for the right range, I obviously check the minimum value. If the minimum value is greater than right, that means I don't have to check that also. And then I check the my requirement, where if the left is within the minimum and right is within the maximum range, and this will just give me the subtree sum value directly. And if both of them do not satisfy this condition, let's say suppose from the left node the left condition is satisfied but the right is not, that means I have to check the right tree also. So here I have to check further. Then if the left and right range are consist this key, that means I can just sum the key, and then I check further down the tree. And this is how I solve the issue. And here you can see that I have fixed range 17 and 34, where it should be returning 75 and it actually returns 75. Now let's go to the follow-up question, where how would you approach scale if each tree update must propagate features for downstream ML models. So I have written that as I have used the augmentation here, I would also use augmentation for that also, because the node will consist all the features. By doing that, it doesn't have to explore all the nodes for the ML models, and it will get instant result from the root. By doing this, we can save the time and scale the tree so that the ML model don't have to waste time. Like for example, for a YouTube video, if a user clicks that, the node will consist the values of watch time, the genre, then the like YouTuber, then the user country, and will store these features, and then it will update the tree gradually, but it won't take time for the ML model to fetch those data as the tree is already updated. So I can scale by using this same solution for upscaling or for scaling the tree to propagate features for downstream ML models. Now moving on to the second question, that suppose you must store and retrieve large model weight files distributed across a database. Explain how a B tree supports fast search and insertion operation at scale. So let's move on to the concepts first. Let me erase this. So a B tree is like a no, it's not like a binary tree, but it's a tree or a data structure where the node does not have a single key, it has multiple keys. So it will consist like 20, 15, 5, 10, or these multiple values. By doing this, we are actually decreasing the levels. That means that it can have multiple next node, and those also have multiple keys also. By doing this, the level are decreasing and the tree's depth is within the range. So as our question asked that for large model weight files, how can I distribute the weights in the database? So by using a B tree, if I store the large weights in with a condition that will store right here. So suppose I have a very large weight and I have to go through multiple values, but doing this data structure, the large weight will just go from this level to this level. But suppose we used binary search trees, then the level would be much bigger. Then it will go through like to the nth of the it had to go to the nth of the level. But here we don't have to do something like that, because our level are decreased because how we managed our data by insertion and deletion. So by inserting the values with a specified condition, we can decrease the space, or we can decrease the time and manage space, as each node is assigned to a block. So a block does not take much space but is a fixed amount. By that means that using a B tree actually helps to decrease the time to retrieve large model weights, and it also helps us to store the large model weights. Now moving on to a follow-up question, that how does this apply to a feature vector lookups in a recommender system? So the recommender system actually have to store multiple feature vectors to recommend a user by using their data. So a recommender system has millions if not trillion feature vectors, which is true. Like YouTube has or Facebook has millions of users, so a million of users has millions of features, and it makes the feature vector trillions. So it actually have to be stored in an efficient way, so that if we search, it can respond within a millisecond, because as a user we obviously want to get a responsive website or a responsive database. So a millisecond matters. So to look up a specific vector, it uses a key. So as I mentioned earlier, that we can use multiple condition based search up, and for the recommender system we will use key to directly look up rather than scanning through the whole tree. By doing that, we don't have to scan through the whole tree, but we will just follow our specified rule, and that is the specialty of B tree. Now moving on to our third question, which is outline an algorithm for finding the minimum spanning tree in a distributed system. Okay, so at first let's go through that what is a minimum spanning tree. Let us erase this. Suppose that we have a tree, not doing this, it is connected like this, it has these nodes, then it has these nodes, and in real world the nodes are actually connected like this. It is this node, then it is this node, this node, this node. So by doing this, we can see that this is a real old sensor model, because our sensors or our Wi-Fi routers or our network system are connected like this in real world, and we have to consider that it can create a graph which is continuous, or which is like which created a circle like this. Suppose here you can see that here it created a cycle, and the cycle actually it can cause repeat and use and can cause up various extra time. So we have to bring out a main tree or the skeleton of a tree which takes up the most less time than other roots. So to find that, we have designed an algorithm. So my main concept was that suppose I have a graph, and then what I will do is I will go through each component, and find the cheapest. Suppose this is the cheapest route. Find the cheapest route and then assign it to a different dictionary. So for suppose this is sensor A. So for sensor A, I will save that sensor A cheapest route is to the C or the cheapest H. And by doing that, I will find the cheapest route for all the sensors. So for B, it goes for B. Suppose it goes to D. For C, it goes to F. So that's how I thought that if I find out that what is the cheapest route of each node, then I can execute my next plan, which is then I will just connect the cheapest route which spans through the whole route. Suppose these are the cheapest path, and yeah, it's done. So this is the cheapest route. Then this brings my tree to very small size. Yeah, that's the design. So as you can see that the tree is much more compact and efficient, and is the lowest costing path for a system, and that's how I designed my algorithm. So let's see the code. Here as you can see that I have wrote example A, B, C, D, and they are connected with their weights. So I have used 3 outside function where I will detect cheapest H, then I will merge as I showed you earlier that how I thought that I would merge the tree after finding the cheapest H of each sensor. Then I will also check the route, like if I even though I found out the cheapest route, I also have to find that what is the route of that node. So for the algorithm, here you can see that I ran the algorithm till the size or the remaining sensor is 1. Then I then I held a dictionary, or I opened or declared a variable for the cheapest dictionary. Then I ran through the sensor graph, then I found the cheapest H. Then I checked if the cheapest H is not none, because there couldn't be a cheapest H, right? That means it is not connected with any other nodes. That's why if the graph is disconnected, then there's no point in checking the graph. So after that I have stored the cheapest H for each node. Then after that, for the final graph or the final skeleton of the graph, I have gone through each H in the cheapest dictionary and then merged, and if the merged is not none, like here in the merge function, I am detecting cycles and merging the remaining skeleton by using the root finder. Yes, I merged by using the root so that there's no cycle in between the skeleton. Then after declaring the edges for each sensor, I am just removing the count. By doing that, my while loop is running through that. So that's how I designed my MST build function. And the follow-up question was that in what real ML scenario would you use MSTs? Yes, as I have told you earlier that for sensor network or for like Wi-Fi router or like our network system, we and our ISP uses this kind of system where the graph is connected in multiple ways in multiple paths, and MST actually helps real world machine learning scenarios too, by finding out the lowest costing path for widely connected network without any loop in distributed system, because we obviously deleted or obviously ignored the cycle. That's why in real world ML scenario I would obviously suggest to use MST, as we cannot use redundant values again and again, as we have to be efficient to run our models. Now moving to our question 4, for a tree or graph based feature index in a memory constant environment, compare slab allocation versus garbage allocation. Okay, so let's consider first. Let's first understand what is slab allocation and what is garbage collection. First we remove the area. Okay, so slab allocation is that we already have a predefined memory block, then it is chopped to slots, and if a new memory comes, let's say this is a new memory or new data, it already has a predefined slot. So if another data comes, it already has this. If another data comes, it already has this. So we manually fix the slot for upcoming data, and it is very hard for developers to assign those, but it is actually very time saving, as it has zero latency or very much predictable latency, as we know that where the data is going. So when we remove the data, let's say this memory data has been used, then we refurbish the slot, and now it's available for our next data, and it's a very good way for real world ML application. And garbage collection is, let's say that is the memory, and the memory comes and it is, let's say, occupied here, let's say this is occupied, this is occupied, this is occupied, then it goes through the whole memory and checks what is unused or haven't been used for days, then it removes those data, and then it makes spaces for new data. It is an automated system. Obviously developers are prone to use those, but as our question mentioned that we have a memory constraint environment. So to compare with our real life example, let's say that we have a room and we already have assigned places where to put up clean clothes, where to put up dirty clothes, where to put up clothes that have been cleaned right now. But if we hire someone, that means that for that person is also present in that room, that means that person takes up a space. So the garbage collection actually takes up a certain space from our system, and this is not very ideal for our garbage or our memory constant environment, which is why for a tree or graph based feature index in a memory constant environment, I think slab allocation is the most suitable process for this environment. As I have written here also that slab allocation is a method of predetermined slot for upcoming data. This is a I wrote this in very professional way, but I am now explaining you so that you can understand that how I wrote these points from my visualization. Then the follow-up question was which option better supports predictable latency for online serving. Yes, as I have mentioned earlier that a single millisecond matters for a ML system, so that means the slab allocation actually better supports predictable latency. As I mentioned that we have already allocated the location, then the latency is predictable because we know that where it's going and how it's using the process for each second. And but the garbage collection, we cannot predict the latency because it is an automated feature and it also use up memory, which is why I think that step collection obviously supports the predictable latency for online serving ML system. And this is how I thought each question should be answered. And Thank you for staying with me. Assalamu alaikum.